Hi. നമ്മൾ ഇന്ന് ഹാർമോണിക് ഓസിലേറ്ററിന്റെ രണ്ടാമത്തെ പാർട്ട്, ദ എനർജി ഓഫ് ഹാർമോണിക് ഓസിലേറ്റർ. For a harmonic oscillator, നമ്മൾ കഴിഞ്ഞ ദിവസം പഠിച്ചതാണ്, the displacement is represented by x is equal to a cos omega t plus phi. And on differentiating, we get the velocity v or the x dot, or the velocity v is equal to minus omega a sin omega t plus phi. This is the equation of displacement of harmonic oscillator, and this is the equation of velocity of harmonic oscillator. Now, for the moving oscillator, the two types of energy. The oscillator is displaced from the mean position, or it is in a strained state. That is, it possesses a potential energy. Also, it is in motion. It possesses the kinetic energy also. That is, the two types of energy possessed by the oscillator are the kinetic energy and the potential energy. We have the relation between force and potential energy in case of a conservative force field. F is equal to minus du by dx in one-dimensional case, or potential energy U is equal to minus integral f dx. U is equal to minus integral f dx, or the potential energy U is equal to F, we have it is minus kx, or we have it is integral kx dx. And here we write integral du as U, taking the mean position for x is equal to 0 position as the reference position of the potential energy. We take the potential energy at that point is 0, and then we have U is equal to, we substitute F is equal to minus kx here, and the limit of integration from 0 to x. That is, the potential energy of the harmonic oscillator U is equal to half k x square. This is the expression for potential energy. U is equal to half k x square. And we have x is equal to a cos omega t plus phi. Then we can write the equation of potential energy as U is equal to half k. Instead of x, I write it as a cos omega t plus phi, and x square becomes a square cos square omega t plus phi. This is the equation of potential energy in terms of time, because it is omega t plus phi, and this is the potential energy in terms of the displacement. That about the potential energy of the harmonic oscillator. That is the potential. If we take the reference point of potential energy as the equilibrium position, the potential energy of the harmonic oscillator is U is equal to half k x square, whereas the function of time U is equal to half k s square cos square omega t plus phi. From this equation, it is clear that with respect to time, the variation is again periodic. This cos square function we will discuss later. This is the expression for potential energy. Any potential energy യുടെ രണ്ട് ഇക്വേഷനും തൽക്കാലം ഇവിടെ സ്റ്റോർ ചെയ്യാൻ പോകുന്നു. The kinetic energy, the oscillator is in motion, and the kinetic energy of the oscillator is given by Ke is equal to, or I represent it as T, for Ke, the kinetic energy T is equal to half mv square, the familiar expression, and substituting the value of V, it has we have V as minus omega a sin omega t plus phi. Substituting that value, we have kinetic energy is half m omega square a square sin square omega t plus phi. With the substitution, we have omega square is equal to k by m. Last class will discuss it. For k is equal to m omega square. With that substitution, we have the equation of kinetic energy T as T is equal to half k A square sine square omega t plus phi. This is the expression for kinetic energy in terms of time. That is, kinetic energy also varies, or it is a function of sine square omega t plus phi. And this sine square omega t plus phi, we can write this as we have x is equal to, again x is equal to a cos omega t plus phi is equal to a cos omega t plus phi. That is, cos omega t plus phi is equal to x by a, or cos square omega t plus phi. Cos square omega t plus phi is equal to x square by a square. And this sine square omega t plus phi, you can write it as 1 minus cos square omega t plus phi. Sine square omega t plus phi, we can write it as 1 minus cos square omega t plus phi. That is, sine square omega t plus phi can be written as 1 minus x square by a square. And with that substitution, the kinetic energy, we can write it as, this kinetic energy, kinetic energy energy T is equal to half k a square multiplied with, instead of sine square omega t plus phi, I write this as 1 minus x square by a square. That is, the kinetic energy T equal to half k, the kinetic energy half k into a square minus x square. This is the expression for kinetic energy in terms of position. This is the expression for kinetic energy in terms of time. So, we have potential energy discussed. Potential energy equation. Kinetic energy equation. That is, potential energy and kinetic energy in terms of position and time, the equations are short. Displacement and expression of kinetic energy in terms of time, also for potential energy. And in order to find the total energy of the oscillator at any instant, the total energy, we have total energy is equal to, total energy is the sum of kinetic energy and potential energy. In terms of position, it is half k x square plus half k a square minus x square. And on adding, we get it as half k a square, that is the total energy of the oscillator is independent of x, it is a constant. Or in terms of time, if you consider the equation of in terms of time, one is half k a square sine square omega t plus phi and other is half k a square cos square omega t plus phi. On again finding the total energy, you get it as half k a square, that is the total, and the potential energy and the kinetic energy of the oscillator changes with respect to position, but the total energy of the oscillator remains a constant. In position equation of equilibrium position means x is equal to 0. From this equation, it is clear that when x is equal to 0, the potential energy is 0 and the kinetic energy is maximum, that is half k a square. And at the extreme position, when x is equal to a, substituting here in the expression of kinetic energy, x is equal to a, the kinetic energy becomes 0 and the potential energy is maximum half k a square. That is, at the mean position of the oscillator, its energy is purely kinetic. The total energy half k a square is kinetic. And at the extreme position, the energy is purely potential, and that is equal to the total energy half k a square. And now if you plot the graph, ഗ്രാഫുകൾ നമ്മൾ ഇനി അനലൈസ് ചെയ്യാൻ പോകുന്നു. എനർജി ഗ്രാഫ് നോക്കുക. ഫസ്റ്റ് വിത്ത് റെസ്പെക്ട് ടു എക്സ്, അപ്പൊ ഞാൻ എക്സ് ആക്സിസിൽ ഡിസ്പ്ലേസ്മെന്റ് എക്സും എടുക്കുന്നു, വൈ ആക്സിസിൽ എനർജിയും എടുക്കുന്നു. പൊട്ടൻഷ്യൽ എനർജി ഹാഫ് കെ എക്സ് സ്ക്വയർ, ദ ഗ്രാഫ് ഇസ് എ പരാബോള, മീൻ പൊസിഷൻ 0, എക്സ്ട്രീം പൊസിഷൻ മാക്സിമം, therefore the graph like this, ഇതായിരിക്കും പരാബോള. Similarly for kinetic energy, half k a square minus x square also a parabola, and this is the variation. But and the total energy is the sum of these things, half k a square, it is a constant. variation of potential energy, kinetic energy, and the displacement. Sorry, the variation of potential energy, kinetic energy, and the total energy with the displacement is shown. Now the variation with the time, one is sin square omega t and plus phi, and other is cos square omega t plus phi. The total energy is constant. And now the variation of the energy with respect to time. This is the variation of kinetic energy, potential energy, and the total energy with the time for the harmonic oscillator. That about the energy. അപ്പോൾ ഓർക്കുക, ഒരു ഹാർമോണിക് ഓസിലേറ്ററിന്റെ the equation of potential energy, kinetic energy, and the total energy. അപ്പോൾ അടുത്ത വീഡിയോയിൽ നമ്മൾ the average value of energy കാൽക്കുലേറ്റ് ചെയ്യും. അപ്പോൾ നിങ്ങൾ എനർജിയുടെ എക്സ്പ്രഷൻ പഠിക്കുക, ഗ്രാഫ് പഠിക്കുക, potential energy, kinetic energy, and the total energy. Okay, thank you.